Good morning, everyone. Welcome to the seminar series of IvS. Today we have Yannis talking about instrumentation as science. Interesting. Yannis did his bachelor in the Netherlands, I believe, quite some time ago now. I think like 10 years ago, Yannis, come on. Then he moved to Leuven for master studies, did a PhD with us as well, and we are stuck with him for a postdoc now as well. He did take a break from us, I guess, for like a year or so to work in the Netherlands, but then realized how much he misses us and came back. So here's Yannis for you today. He will talk, as I said, about instrumentation as science, and he will use JWST, ARIEL and METIS as an example. Please, Yannis.
All right, thanks, Andrew. I'll just start the meter. Hello, everyone, and I would like to first start by thanking you all for making it through the cold and the snow and the frozen roads. I myself had a bit of a moment where cycling, sometimes, you know, when you take certain turns, it can be a life or death situation. So I'm happy I'm also here in front of you giving this presentation. And also, I would like to maybe start with a bit of a anecdote story, since we're all eagerly waiting for Maria Carey to thaw. There was as Andrew said, I've been here for a little while, and one day I was in the IvS kitchen. I was just eating. I was 3 months into my PhD, and Alejandra Fuentes shows up and says, "I have never heard you speak, let's say, about your own interests and hobbies." And she was like, "But I need to put you in a box, okay? What is your favorite color?" I said, "My favorite color is blue." And she said, "Thank you," and just left. From that point on, I was in a box, okay? Now, it's important to understand the value of boxes, and specifically since blue is in fact not my favorite color, to understand that there's always subtlety into defining people, and in this case, you know, you could talk that I'm working on instrumentation, but that can mean several things. And so I would like to start with a bit of a quick advertisement as well. So at IvS, many of you may know or not know that we actually, in fact, have a lot of different expertise. And you can see here in the middle the astronomical instrumentation group. But what you may not know is that we have, in fact, a lot of people at IvS who may not be doing research as, let's say, the typical PhD to postdoc track. But we have a lot of people ranging from mechanical engineers to calibration scientists to project managers to solid-state physicists and lab engineers who are all working with the same kind of bigger umbrella vision to essentially build the instrumentations of the future. Now, if you are interested in instrumentation, I do encourage you to either contact me or subscribe to the instrumentation channel. We have bi-weekly instru meetings, as we call them. I coined the term, but it's really bad, hence the link is clear. And so every time we also give project updates, so if you would like to know what's happening at IvS, I strongly encourage you to sign up. And so I have put here boxes, but these boxes, of course, have names. And some of these people you, of course, have interacted with, some a bit less so. But you can see here for each one of these, there are several people at IvS who are working day in, day out to produce the next generation instrumentation. Now, I'm cheating a bit because you see a lot of names in here, and for example, Gert is showing up in every single one of these. So take that with a bit of a grain of salt, but here it is. And so I do encourage you, if you have any vague interest in instruments and any of these topics that I'm showing here, even data science, for example, or orbital engineering, I do encourage you to follow up, or at least I'm happy to message you when one of these topics gets discussed in more detail. Now, for this talk, I want to split it into 3 parts. Well, we will happily recognize here that I've already finished the first section here, so yay. Now, I would also like to talk, however, about the overview of James Webb, ARIEL, and ELT, specifically the METIS instrument, and also my role and responsibilities in these missions, because I finished, as Andrew said, I have finished my PhD a little while ago, and since then my role and the type of work I do doesn't really fall into those boundaries or boxes of classical research, and it's a bit more into the management side. But I would like to talk a bit about the latest work I did during my postdoc about pushing the calibration accuracy of JWST, specifically the MIR instrument. And that's with the goal to allow for a new type of, or expanded scientific domain of mirroring. And then part 3, I'll talk about the core of my work, that is now preparations for the ARIEL and METIS ground test campaigns. And I'll explain what goes into that. Now, for those who have not heard of the James Webb Space Telescope, you must have been living under a very big rock. And it's actually funny because we do transits, right? So if you think of the Earth as a rock, for aliens, we're like an exoplanet. So I think it's nice that you have been living under a rock. I think it's of scientific value to other civilizations out there. But for more specifically for the type of science that James Webb has done, a lot of it has been in covers of Nature and Nature Astronomy and Science. And I'm very humbled and pleased that all of these papers are essentially done in collaboration with a lot of the colleagues that I've worked with over about almost a decade now. But for today, I wanted to focus a bit more on the exoplanet side of things. So here, this cover was called Brave New Worlds, and essentially we're trying to push our understanding of other worlds out there using the extreme sensitivity of James Webb. Now, I always have to also give a bit of an introduction on how we actually study the transit, the exoplanets, and most of you will know this. We talk about usually transits and phase curves. And so here, if you imagine a solar system, whether it be our own or one out there, and you have a planet that passes in front of the star, when it does so, you will see a dip in the light because of the light that is blocked by the planet here. And then you will get another dip when the planet is in fact behind the star, and so you only see the light or the flux from the star itself. Now, a secondary aspect to this, which is also of great interest, and we have been able to calculate and measure and put error bars on a lot more accurately, is the so-called change in the amount of infrared light as we go around the orbit. And the reason for that is that, as you can see in this kind of basic schematic, you can see that here we look at the night side of the planet, while here we are able to see both night side and day side. And that means that there's a difference in temperature between the two sides, which we are able to probe in our measurements. And by doing so, we are able to actually build a so-called phase curve that shows the profile across the planet of the, for example, temperature profiles and pressure profiles as it's orbiting around its star, which is a very powerful tool. Now, if I were to focus mainly on the transit here for the type of first science that is coming out of James Webb, I'll admit the labels are a bit small, so I'll just go over it with you. So here it's wavelength of light in micrometers, and here on the y-axis you have the amount of light blocked. Okay, so that's basically, if it's higher, more light gets blocked. So what you are seeing here is that as we are looking at near-infrared wavelengths, we have different wavelengths resulting in different amount of light that is blocked. And so that is basically because of the molecular content in that atmosphere, where different molecular bands, such as water or carbon monoxide, or potassium here on the left-hand side, or you can also have carbon dioxide here at longer wavelengths, they manifest and they show features in different parts of the spectrum. And so that's why spectroscopy is so powerful, even though it doesn't always make for the prettiest images to look at in these like two-dimensional covers. And so one important aspect that I want to cover from this slide and that I want for you to take away is that you can see here that these are three different instruments and 4 different settings. So you have NIRIS here, it's near-infrared spectrograph at the very short wavelengths. Then you have NIRCam here that has it uses a specific kind of prism to get a spectrum out, even though it's a camera, so that's a bit confusing sometimes. And then we have NIRSpec at the higher resolution, so you can see here that the number of data points over a small x-axis span is a lot more dense, and so that's just because of the spectral resolution being higher. And then we also have the NIRSpec prism that has a lower resolution, but it covers a much wider wavelength range, allowing us to probe many more of these features. Now, the trick here is that because we have these separate panels here, if we were to actually put them all in the same plot, you would in fact find small discrepancies, okay? And that is because calibration always comes into this, and we always need to understand how our instrument affects the light as it comes onto our detector and gets translated into electrons. And now, going from electrons back to the actual photons that come from these stars and get blocked by the planets is a very sensitive process, and it can often result in some uncertainties, which we are always continuously working to improve. But that is also why we usually show different instruments in different modes in different panels, because if we were to put them on the same, you would see, for example, a vertical offset, which is very common between nearest and near spec, and that's because we're continuously trying to improve our calibration. Now, for ARIEL, this ideally, let's just see, okay, famous last words, but ideally we will not have gaps or offsets, and the reason for that is that ARIEL will take instantaneous spectra. So what that means is that they will have a set of filters that will essentially split the light into different detectors, but it will all be the same beam that comes from the telescope, goes through the filters, and then produces a end-to-end 0.5 micron to 7.8 or 8 micron spectrum. And that is important because essentially any differences between chunks of light can in fact affect your determination of the molecular compositions of those planets. And even more so, now that we recently have started to look at non-equilibrium chemistry, this can affect the kind of pressure and temperature profiles that you're deriving as a function of scale height or your atmospheric height. So again, the spectrum here, so for example, one spectrum here, would then result in one profile. But then if we look at an exoplanet in a different phase, so this green one here and the red one are just a different phase in the orbit, so a different location in the orbit, you would see changes because of the, as I described, the temperature. And so in that sense, we are able to probe different parts of the atmosphere. And that's why it is extremely important to have continuous spectra like this. And so that will be the power of ARIEL. Now, for METIS and the ELT, METIS promises all of the things, but more specifically, it promises an extremely high contrast in terms of spatial contrast. So how close can you detect nearby companions to the host star, for example, that's in the solar system? And secondarily, the spectral resolution or the velocity resolution will also be very, very large. So here what you are seeing is the system SR21, where it's approximately at 150 parsec from us. And so if we translate the angular resolution in milliarc seconds that METIS will be able to provide, and we put the numbers in, we know that there is a gap here at around 6 AU, which is about the orbit of Jupiter, that we would be able to directly observe. Okay, we're not talking interferometry, we're talking about direct observation. By blocking the star here, you would be able to see this ring and potentially any sort of planets that are forming there. And so that is extremely interesting because, of course, the push for this Earth 2.0 to get to that 1 AU is continuously ongoing, and we're continuously improving our instruments and building bigger telescopes, which we can argue about whether that is the right approach, but that is extremely important. And the secondary aspect to this is that you can see that there's a ring around this target, and so what you're seeing here is this kilometers per second, that's the radial velocity, so we are able to probe the material that is coming towards us and that it's going away from us. And so this allows us to form a geometric picture of that dust ring around the star, which is again important for the formation processes arguments. And so I just want here to finish a bit with this first part with a mission comparison. For all of you to have just some numbers to take away, I suppose. Here for the primary mirror size, we had 6 meters, but segmented. As you can see here, the different segments that are onto the James Webb mirror. Then for ARIEL, it's a monolithic mirror, so there will not be any needs of like using actuators to bring the whole light in phase. And then the last part is again 39 meters, which is extremely large, which is in fact the acronym. Great. We lack inspiration sometimes. Now, the second part that I would like you to take away, though, is this argument here. For James Webb, it's a wide wavelength coverage in the near infrared and mid infrared, but we have separate chunks. While ARIEL will have simultaneous spectral coverage. And that is really the push for this, where we will be able to observe 1,000 nearest exoplanets with ARIEL as a dedicated mission. And then finally for ELT METIS, it's a shorter wavelength range, but with extreme resolution. But yeah, it will be again kind of separate chunks. And so for the numbers here, it's not that I think you can interpret it as the larger the number, the better, I suppose. But it's also about essentially understanding how we would be able to find very nearby companions, very faint companions, and also look at the radial velocity profiles for different, not just planets, but all kinds of science cases. And so the technical aims effectively for Webb were to observe the faintest signatures out there in the universe. Then for ARIEL, it's driven by extreme stability. So we want everything to be unmoving and solid. And then for METIS is a strive for the highest contrast. One thing that I, of course, forgot to mention here, another reason why it's separate segments here is, of course, we have the Earth's atmosphere that captures some of the photons at certain wavelengths. And so that's also a necessary limitation. And so finally here for the mission lifetime, it's 6 years, so we're already sort of halfway there for Webb. Then 4 years nominal lifetime, and ELT is forever. At least that's the science pitch. Now, for the next part, I would like to talk a bit about my roles on these different missions. And that's not because I want to basically, give an autobiography here. The point is that this has affected very much the type of work that I do. And so that's why I would like to, both myself and the audience to appreciate the difference in the research that I'm doing here. Photos. So this is basically, I finished my PhD thesis on the James Webb mirror calibration in 2021, so that was 3 years ago. And during that time and also afterwards, I was very happily working as an instrument scientist for the spectroscopic mode, the medium resolution spectroscopic mode of MIRI. But during that time, I was also talking about being able to escape your office from time to time. I was able to go to Baltimore in the US, where as part of the commissioning team with all these wonderful people, some of them were not here, we're not there, and so we put little cutouts of Bart here, who is not in the audience, so that's disappointing. That serves you right. And so we very gratefully use the library, in fact, of the Space Telescope Science Institute to do our work on a day-to-day basis. And we're all smiling here. It was very hectic, I assure you, but I don't know, something about a nervous smile that creeps up when you have to take a photo. And this was the mission control room here with the computers where we had all the telemetry from Webb. And back there, this person you can see was called MOM, M-O-M, the Mission Operation Manager. But whenever we had to ask a question, we had to call MOM. Yeah. Now, my role on the ARIEL mission, this is a bit more, I suppose, managerial again, but that's kind of the reality of it. So I'm showing here on the right-hand side the kind of schematic of the contributions from the different countries to the ESA ARIEL mission. And so you can see that most of them up here for the system core team have the UK flag and some of the Italian flags up there. So all the system leads, engineering leads, etc. And so there are contributions from all across Europe, in fact, for everything else, some subsystems as well. So two of the important ones, I would say, would be more of the spectrometer and the fine guidance sensor on ARIEL. And so there is also like two Belgian flags. One is from CSL, Stefan Roos, who's working over there. And then for the calibration working group lead, the second Belgian flag has my name on it, which unfortunately comes with responsibilities, which I have still to muster. But the idea here, so on a day-to-day basis, what do? I coordinate a team of 20 engineers. Most of these are in fact in this sheet, and so they are spread all over Europe. A lot of them in France, and actually speaking French comes in as a surprising advantage when you're dealing with French people. And so I will not elaborate, feel free to ask me later. And so two of the major contributions here is that I'm planning the tests and the test definitions that need to happen for ground and flight commissioning, and also I'll be leading the ground test data analysis for requirement verification, which sounds very technical, but there's a lot of things to be learned for the science that will come out of ARIEL. For my role on METIS, I am the METIS instrument performance testing lead, and so you can see here we're actually two of us. So there's Roy van Boekel, who is in Heidelberg, MPIA, and myself, and I would be contributing not just on the planning of the test and definition similar to ARIEL, but as you can see here, it's not just the performance testing, but it's the performance test plan as well, writing the commanding scripts for how the instrument will be operated in a different configuration, etc., and then also organizing the data. I wish it was just folder management, you know, and performance analysis as well. And so I interface with the subsystems. What does that mean? It means you have an imager, spectrograph, high contrast imaging, worm calibration unit, pipeline, and data storage teams on a daily basis. And that means that I do a lot of telecons, which is absolutely great. And so the leading of the ground test data analysis efforts, which will happen over the next 3 years in Leiden, is going to be a big part of that. All right, part one done. Great. The second part here, I would like to talk a bit more on the classical research that one might envisage. And so at the time when I finished my PhD, as I said, about 3 years ago, there were still several big challenges, and I put here 3, but this is a lie, there were many more. But these, it's just for digestibility. So the first up here that I would like to present to you today is explaining a significant broadening of the MIRI spectrometer point spread function, and I'll explain what that term means. The second part was about modeling extended structure around the point spread function, and so spoilers, that's very complex, and I could give another seminar about that. And then the third part was about correcting interferometric fringes, which in fact was presented in the seminar of Danny Gassman, and I do recommend, if you're interested in that effect and you're working with James Webb data, MIRI, to go and watch Danny's seminar on YouTube. Now, focusing on that first part and actually giving a bit of a 101 in point spread function for those who might not be dealing with astronomical data a lot of the time. So if you think in very simple terms, you have your sky image up there of let's imagine a crowded field with stars, and then your optics, basically the biggest contribution is the primary mirror, introduces a sort of response function to that by which you are convolving. And I put XY here. You can put your favorite celestial coordinates in there or detector pixel coordinates. But the important aspect to this R function here, for a circular mirror, it will look like an airy disk, which is this type of function. So a bright lobe in the middle and then secondary waves out there. And then this will essentially vary, but it's symmetric across your focal plane or detector if you want. Now, if you have a bigger primary mirror, essentially this airy disk will be a lot sharper, okay? So the width of it will be a lot narrower. And that is the one parameter that affects it. The second parameter is wavelength. So at longer wavelengths, because of diffraction, we get a broader response function, and that means that things get blurry, at longer wavelengths. It's as simple as that. Now, you would think that with wavelength and diameter, it's solved. We understand the diameter of Webb. We understand what wavelengths we're observing, so we are happy. However, I told you that there's an unexpected broadening linked to that. And if I were to show you a little graph here with actual points, I should have made a scatter plot. I apologize. I'm showing here this R function, so specifically the full width of max, by which I mean the width of this airy disk, okay, in pixels. And then on the x-axis, I put time. Now, what you're seeing here is that as a function of time, it looks like our response function, so this, or what I call point spread function, is getting broader. And so that was a bit of a conundrum because it's immediately makes you think that the longer you expose, which is the way most people approach it to actually get a higher signal, the worse your response gets. And so that's something that we need to better understand. And so in order to understand this better, in fact, I used the Poisson CCD package. And so this solves a electrostatic potential equation given here. So it's a second order differential equation where you have the accumulated charge density as the rho symbol here. And this is just the constant, the dielectric constant of silicon. Now, What I'm showing on the left-hand side is the detector plane, where you see several squares. Each one of these squares represents a pixel, and each one of the values in that square represents a bias voltage. It's basically a difference in potential that you introduce in order for the electrons that are captured to move to the pixel. Okay, so this value is constant. So if there's no incoming light, everything's fixed. It's beautiful. Now, if we inject 20,000 tracers, so imagine you're bombarding your detector with photons over a certain point spread function. Okay, so over the ring, the airy disk that I showed before, I just randomly select locations and with this normalized distribution, and then bombard the detector. What you're seeing then, I color with red the electrons that actually move to the same geometric pixel above which they are detected. Okay, so one red dot here means that it went straight down, and then the black ones are just a different color to symbolize the neighbors. Now, on the right-hand side, I'm showing a cross-section in X direction, okay, and then I show in Z direction the thickness of the detector. Okay, so we have a detector substrate, and it has a certain physical thickness. And what you're seeing are the photons being converted to electrons up here, and then zooming all the way down. So far so good. Everything's beautiful. We have we have observed a small amount of photons, electrons, and now we crank it up a notch, and I'll change the injected number of photon tracers by a factor 15. And now what you are seeing is, because of the charge accumulation, the electrostatic potential in the detector has changed. You have introduced electric charge, and that electric charge is changing the end-to-end potential. And so these are represented here by the change in the values. So further out, it's still 2. Closer in, it's a more negative value, which is actually approaching our absolute ground limit of -4. And what you are seeing on the right-hand side, if I blink between the two, is that now all of a sudden it seems that there are fewer of the reds that actually land in that geometric space that we were looking at before. And you can actually see also here some of the paths of the electrons curving away. Now, what is happening is that because of the central pixel having accumulated a larger amount of electrons, the change in potential is much larger compared to the neighbors. And so this essentially attracts the electrons to the neighbors over here, and that will result in a broadening of your point spread function, okay? Because instead of detecting the electrons here in the middle of the airy disk, you're detecting them at the edges. And of course, as a function of time, you're accumulating more and more. And so if we go all the way to the kind of more extreme case, you can see that the largest fraction of your electrons, in fact, go to the neighbors. And that is how your PSF gets broader as a function of time, which is in fact not a function of time. It is in fact a function of your charge density, accumulated charge density. Now, why is this important? We talked detectors, electronics, potentially it doesn't really combine with science very well, but in fact, I'm showing here work done by Sandrine Juillard in collaboration with Danny and myself, where in the center here you would have a host star, a very bright point spread function, and in fact there's a faint companion here next to that, where without correcting for the effect that I was showing you before, it is actually a lot more difficult to detect it with a high level of accuracy. And so it is even more interesting when you consider that in fact some of these planets that are known or neighboring faint companions may in fact also host circumplanetary disks, which is an entirely observationally unexplored domain, because we have been able to derive some concentration of the dust in those disks, but not the gas chemistry with all the features like the usual water, carbon monoxide, dioxide, sulfur, etc. that we're interested in. And so if we are able to remove the point spread function and all of its systematics accurately, we would ideally, hopefully be able to also study the gas chemistry in those companions. And so that shows that indeed a better calibration can open the way to new and exciting science, and we're really pushing for this forward. This is still preliminary, but we're hoping to have nice results to show soon. For the third part, it's about the prepping of ARIEL and METIS ground test campaigns. And here, the fun is over. Okay, now we are no longer having fun. We're talking timelines. For timelines, this is essentially, I could plot this as a graph of stress over time, okay? But instead I have chosen to just put milestones here. So both ARIEL and METIS, I'm working on both of these projects 0.5% of my time, which my time is limited to 24/7. And so what I'm showing here for ARIEL in purple and METIS in green, I'll try to go over them separately. So if you can, try to focus on the purple stuff up here. So right now there's instrument testing happening, so both the spectrograph and the fine guidance sensor, as I mentioned. So this FGS is being built in Poland, the spectrograph is in Paris. They're going over their instrument level tests. So that means that there's it's just the optics on an optical table, optical bench, then they put them in a box, and then that box they will ship to the UK, where it will be combined with the mirror. Now, this combination with the mirror, we in fact have two versions. Okay, so for instrumentation to work, we have different models. So we have the EM model, that's an engineering model, and we have a flight model, which is FM. Now, the engineering model, you can go in with a hammer and hammer it until it breaks, and then you're like, I've tested it. Fantastic. Now, for the flight model, you are not allowed to do that, disappointingly enough. But it means that you should have the best idea, whether it be engineering model or those that know more. It's also you have the qualification model. But essentially, we should be able to test everything end to end for the engineering model and really understand as well as possible the measurements and instrument, where this will kind of start around February 26. And so there will be a long period of analysis of the data that will allow us to understand how to best operate ARIEL, the instruments, and the end-to-end telescope mechanisms as well, so that we are essentially ready at the time of the flight model campaign in January 27 to do a smaller section of those tests and analyze the data, so that we are then prepared once we launch to have this commissioning phase similar to Webb, and do the analysis and then provide the first beautiful data of transits and phase curves of exoplanets that are out there with people hiding under rocks. Now, for METIS, we have here the green arrows, so try to focus on the green font now. So in mid-25, actually a bit earlier than that, we will have the start of the system level, assembly, integration, and testing. Okay, so the verification happens later. Where the first components, so the crowd chamber, support structure, one calibration unit, common for optics, will be arriving, and so that's when we start doing tests. Later, the spectrometer will arrive and the imager, and by the time we have finished everything, after 3 years, we'll ship METIS to Chile, where it will be combined with the ELT, and we'll have an assembly, integration, and verification campaign there, which promises to be exciting, and I'll be there taking photos with my good friends and showing them to the next audiences at the next seminars. Now, I wanted to talk about some of the challenges that we are facing for ARIEL and METIS. And so 3 of them that I put here are in fact the slightly most annoying things that we have to deal on a day-to-day. So the first thing here is that the test facility, which will be at RAL, which is the Rutherford Appleton Laboratory, it's close to Oxford, a very short bus ride, will only be able to illuminate 1/4 of the primary mirror of ARIEL. Now, if this was a lecture for the students in instrumentation, I would ask, what does 1/4 of the primary mirror illumination translate to? And the correct answer would be that the point spread function will be a lot larger. Okay? And so this has implications, as I will talk in a second. The second part is that the time available at the test facility is very limited, and that is because money is limited. And in some cases for ARIEL is not James Webb. ARIEL has a limited, much more limited budget, and so we need to understand that ARIEL will go in, we need to do the test, and we need to get out, okay? The next satellite has to go in. And so that's basically a question of maximizing efficiency then. And then the third part is about a missing role of an expert to define the focusing strategy using the secondary mirror mechanism, which is also fun, as I'll talk in a bit. Now, I already gave the spoilers, so the issue with this first aspect, that we are not illuminating the full mirror of ARIEL, essentially translates to the following. So if you had a fully illuminated mirror, your point spread function, so there are some black circles, and that's why you cannot really see the yellow that well, but essentially the point spread function is very small, and we are able to essentially compare with the performance that we would have when we are in space, okay? So think of this as ARIEL is in space, we get this data. On the ground, we'll get the image on the right-hand side. So this is essentially a 4 times larger. So the first ring here is, you can think of it as 4 times larger as the one over here. And so the light gets spread over more detector pixels. Now, specifically, why is that a problem? The first thing is that we cannot directly translate the performance that we are measuring on the ground to space, okay? So I mentioned that we have this larger point spread function. We also have the effect of gravity here. But the point is that if we are not able to translate those measurements that we will be taking, the first thing that one can say is like, oh, they're useless then. No, they're not, because we understand our physical models, and using these physical models, we can correlate the measurements. So we introduce in the physical models this broadening or this effect of the quarter aperture illumination and gravity, and then we are able to do the comparison there at that level. The second thing is that we are less sensitive to defocus and misalignment, which is in fact a key goal of the test campaign. So you really want all the detectors, so for example, the fine guidance sensor and the spectrometer, we need to know exactly, if we move a little bit the mirrors, where is the beam going between the two. And so if you have something that's much broader, and you imagine of fitting a Gaussian into this or whatever, the fact that it's broader, in fact, makes you less sensitive to this movement and also to the width of the profile. And so that's something that we need to account for as well. And so the last part, of course, that the signal that would be on 1 pixel is now over multiple pixels, and so you need a larger amount of time to get the same signal-to-noise ratio or accuracy on your measurements, which translates to how well you can verify the requirements. And so this is not all doom and gloom, of course. So as I said, we developed those simulated models, and we perform similar tests at instrument level. What do I mean by that? Is that at instrument level, we are able to block part of the light, and then we get the same effect on the detectors, okay? And then this is kind of a similar thing that allows us to get some useful insights. The second part here about defocus and misalignment, we verify via calculation how sensitive, in fact, we are, and that will allow us to know, okay, what is our strategy then? And then finally here, it's about the iterating for the test planning in terms of knowing if we need to cut some tests or spend less time on other tests. That's basically how we can approach this. And now for the second part, regarding the time available in the test facility, as I said, it's very limited. So what I'm showing here is the cool down profile in the cryo vacuum chamber that we'll have at ARIEL, the test facility. And in fact, there are 3 curves here, time versus temperature in Kelvin, because we're looking at different surfaces. So the V grooves is the sun shield of the telescope. The TOB, that's the telescope optical bench on which the telescope sits. And then the M1 is the primary mirror. And you can see that each of them cool down at a different rate. And in fact, the yellow one is the slowest to cool down because it is the largest surface. Okay, so it takes more time. And so in scenario 1 here, you would imagine that all instruments are their operational temperature all the way here at the right after 40 days, which is a long time. Each day costs money. And so we can start the test there. However, now we know that we are limited in time. And so one thing you could potentially envisage is actually say, okay, the fine guidance sensor, the moment it reaches 100 Kelvin, it can already, the electronics are cold enough to allow us to start taking measurements. So we're like, perfect, we can start already doing measurements with the fine guidance sensor. However, you have to understand that although this sounds ideal because we, gain time, in fact, if I'm not mistaken, we gain 25 days of schedule. So everything is solved, math. This is in fact not that straightforward because things are cooling down. The wavefront, the optics will perform differently here than they will perform there. If you measure a point spread function, it will be much broader here than it will be there. So you are in fact in need of still repeating some of these measurements because you will not have your final performance when you are fully cold. And so that's still a caveat. Now for the third part, I'll just quickly go over this. So there's still missing role of experts. So Oftentimes, I imagine myself being able to do everything, but that would not be reality, would it? And so doing it yourself is, is rarely an option when we reach the level of space missions and really expertise. And so given that those are not gained in a month or year, it's important to, in fact, be humble about that. And certain discussions then pop up in one working group. So for example, the calibration working group that I'm leading, you have all kinds of things that are coming in there. We're like, no, this is not our job. It's someone else's job. Like, we don't have the expertise to do this. You need to find someone else. And so it is important because you put your foot down and you just say, this is not possible. This needs to be done by an expert. And so if you care about the mission and the mental load on your colleagues of that working group, you will insist and keep insisting until the management solves the problem and finds a person who has the right expertise for the job. It's as simple as that. Now, for METIS, I'll just spend the last 5 minutes here. Essentially, METIS has, the biggest challenge is that it's very complex, which is both a good thing and a bad thing. It will be able to do amazing things, but it's also has a wide number of configurations, and so we need to be able to test most of these and understand the instrument as well as possible. Then parts of METIS will also be arriving at the integration facility at different times. I already showed this in the timeline, and so that's important, as I will be touching upon. And then the third part is that all interfaces have to adhere to the ESO framework and standards. And standards are important, but there is a specific case where things can get a bit annoying, but yeah, I'll discuss about this. Now, before you all get shocked, because when I put them all on the slide, I was like, oh, did I do this? That's pretty cool. But yes, so what I'm trying to show here for the spectrometer, in order to understand this complexity and boil it down into building blocks or boxes, I guess, you have to create logical flowcharts to show how different tests relate to each other. So what you're seeing here with the cyan boxes, and I'll zoom in to one of them in a second, are performance tests that we want to do. The white boxes show requirements and outputs from that. The orange boxes show calibration data products, and then the purple shapes there show monitoring tests. Now, if we go into just one of them, you have to understand that we do tests in order to verify requirements. That is, at all times, your #1 goal. However, requirements are written by people. People that, at the time of the writing of the requirements, may have had an incomplete understanding of the system, because you learn as you do, okay? And also, in fact, sometimes requirements are, let's say, a bit vague, okay? So we allow for some vagueness in order for ESO to let the mission through and continue on to the next phase, okay? Because if you go into every single nitty-gritty detail, you get feedback on every single destructive criticism on every single aspect, and that's not, in some cases, this is counterproductive. And so all I'm pointing out here is that, for example, you have these requirements here in these boxes, and what I have tried to do is, let's try to verify the requirements, but let's also test things that may not have been reflected into the requirements, because at the end of the day, something might pop up where we're like, we don't understand this well enough and how it impacts other things. And so I appreciate that I'm being also vague to you here, but it's also, this could be this one plot could be, again, a 1-hour discussion as well. And so for the second aspect here that I'll move on to, for the parts of METIS that will arrive at different times. Now, I could be fired for showing you this Excel sheet, but I'm sure none of you cares enough to take a photo. And so you have different phases here. We have the A, B, C, D, E, F. All that means that different subsystems, as I was talking about in the timeline, will be arriving at different times, okay? Start, end here, ready for integration. You have the approximate dates here. Now, the point about this slide is the fact that, imagine the first subsystem comes in, you test it fully. Then the second subsystem comes in. I have talked about cross-calibration between instruments before, and so you need to test both instruments with the same source to make sure that they're consistent with each other. And this adds complexity, okay? You have to repeat measurements, and you have to introduce layers in the planning that are required because you have, also limited resources, time to delivery, cooldown cycles, and the arrival of the next subsystem, which will mean that we need to open the box again, have another Christmas, and then add the next subsystem into that unwrapped box. So the last aspect here was about interfaces. Now this is more about me complaining, okay? This slide is just, standards are a blessing and a curse, okay? They are a blessing because it allows you to follow a specific framework that you know works, and other instruments, the VLT and the VLTI are using this, all the other ESO telescopes are using that framework. However, when you don't know how things will happen at system level, okay, when you're bringing in these components and you want to test things get a bit messy sometimes because you get data that you don't understand. You find stray light, which should not happen. And so this is kind of outside the realm of we call them known unknowns, okay? We know that they might appear, but we don't know how they will appear, okay? And so that means that if we need to both write a commanding script for METIS to analyze that known unknown better, or if you have some data that you want to analyze with a semi-complete data reduction library, that's something we need flexibility for to work on. And so, yeah, basically what happens when something doesn't work, we are currently having conversations to have a hybrid approach, in fact, with offline tools for at least the assembly integration and testing phase in Leiden. Once we are at the telescope, we will have a very good understanding of how METIS behaves, and so there we will have all the framework, everything sorted out, famous last words, and ready to go. And this is my last slide, so conclusion and looking ahead. So this is more of a motivational slide, but yeah, James Webb is producing fantastic data, really. I mean, it has been from all instruments, all modes. They have their niche in the science as well, but it's really producing fantastic new insights into the science fields that James Webb is studying. And so we keep understanding the instruments better, of course, the calibration as well. That takes time, but we are doing our best. And that, I hope I have shown you one simple application, but it really pushes into the modes into new scientific domains as well. And so the sky, in fact, is not the limit. The detector noise and photon noise is the limit, but we are still very much always over-optimistic about what we can do, which is good. The second aspect here was about the physical constraints and the effect of gravity and quarter aperture illumination that I talked to you about for ARIEL. And so this adds complexity, of course, to the testing, but it's also important to understand that we understand the physical models well enough to be able to, even under gravity and quarter aperture, to say, okay, what we are seeing will translate to this performance in flight, sorry. And so for METIS, yeah, it's the complexity again, but we are trying to find which is the minimum number of configuration we can test to have a full understanding of METIS without testing all of them, okay? And try to interpolate, if you will, in some cases, but in other cases, it's really it's just a matter of time. And so we will be continuing the calibration once we are in Chile and connected in Cerro Armazones, as I'm showing you, and connected to the rest of the telescope. And so I just have a little quote here to link back to the title of my seminar. I'm paraphrasing Carl Sagan, which is very not humble of me. But yeah, instrumentation as a science is a collaborative enterprise. Okay, I hope I have, even with a quick advertisement at the start, I have convinced you of that. And so it spans generations, not just in terms of age, but in terms of instruments as well. And so when it permits us to see the far side of some new horizon, we also remember those who prepared the way, seeing for them also. And with that, I would like to leave you here with my good friends from all across the globe, and I would like to thank you for your attention. I went 2 minutes over time.
That's okay. Thank you for an interesting talk. Before we go to Q&A, 2 reminders. One to Yannis. I can guarantee you nobody took pictures here. This thing is going to go on YouTube. Second reminder, I didn't want to tell that before the talk for you to stay unbiased, but now is a good time. Yannis absolutely loves to read and, more importantly, write fantasy. Keep that in mind.
Why did you have to? Okay.
Now we have time for questions.
I mean, isn't this fantasy? All right.
Hi, Yannis. Thank you for the talk.
You're welcome.
Yes. I had a question way back at the start about ARIEL. You say that one of the goals is to be stable, and they enable this by observing all different parts of the spectrum at the same time. Now, you and I know that this does not mean it will be stable or a continuous spectrum.
Yep.
I just had questions like, how many detectors are they using? How is the light dispersed? And how are they going to make sure that actually we do know the detectors well enough to get a continuous spectrum without jumps?
Yeah, so thanks for that. As you correctly said, so we are in fact not talking about a single detector, so it's not like all of the light will reach one detector with one set of properties. We are using 5 detectors, okay? So there will be 2 photometric channels, so that means you just get an image of your field, and then you get 3 detectors that measure spectra, okay? All of these spectra are in the near infrared, different band passes, but the technology of those detectors is the same as what is used on James Webb Near Spec. And so that allows us to use all of the expertise and know-how of James Webb to understand and improve our calibration for ARIEL. So this is one thing. The second thing is that I mentioned filters. The beam that will arrive from ARIEL will go through a set of dichroics. So it's essentially beam splitters that will, you have the white light that arrives, and then it goes through one filter that sends part of the wavelength chunk to one detector, and then the rest onto the other detectors. Now, what that means is that you are also observing the same background and this at the same time. So for Webb, when you take an observation with a specific science mode, you are looking at one part of the sky, then you go on to another part of the sky, you use another instrument, and then potentially you come back. We do see variations of the background with time, because when we go to one place of the sky, you can have zodiacal light, or you have Webb with respect to the sun at a different angle. All of that translates to a different background. However, for ARIEL, we'll have one measurement with one background that we can correct for all of the instruments, and that will be uniform throughout. The third aspect to this, and I understand the argument of being stable, is in fact that the photometric channels with the fine guidance sensor will be measuring variability of the light. That's their primary purpose, besides also guiding, of course. And so that variability that we'll be measuring with the FGS will allow us to correlate to the spectra to find if there is some variability photometric because of this or that reason. We should be able to get a better understanding of the variability. It can also be, the star that's variable, okay, and that's better to do it with the photometers, and then translate that to the variability we see in the spectrum. That's just one way we will be decoupling things in real time. And so those are just 3 examples.
Okay, thank you. Good luck with that.
I'll give another seminar, I promise, on this.
Hello, Yannis.
Hello,
Thank you.
Jamal.
That was
Good.
very clear. I have a question for your James Webb personality.
Okay.
You said something that always confused me when people say it, is like this PSF calibration where you want to, I don't know the verb that you use, but when you want to remove the PSF. I'm always confused because to me, whether you remove it or not, you always have the photon noise from it that is staying, and that's the biggest problem you have.
Mm-hmm.
So what do you mean? I don't remember the slide that...
Okay. I had this slide, I guess,
Exactly,
for the PSF
yes.
subtraction. The point here is that essentially if you are able to beat down the... Of course, each one of these pixels. So, all right, let me show the other one. All right. Now, imagine we could do a perfect PSF subtraction, okay? It means that that image would be absolutely dark. That will never be the case, and that is because there is Poisson noise, of course, as you mentioned, that affects the uncertainty on the detection itself. You are having a detection with a certain uncertainty, and that will forever be true. What you are trying to suppress is the intensity, so the noise properties are still there, but the absolute intensity, which is the square of your PSF, needs to be suppressed in order for the signal from your companion to be above that photon noise, read noise background. And that will, of course, all go into that SNR, which I did not describe, the signal-to-noise ratio. The photon noise from the pixels here that we're measuring the point spread function of the host star will have that contribution, and it has to go into that measurement. However, it will be, we're trying to beat the intensity aspect of the PSF, as opposed to the uncertainty on it.
Okay, so yeah, you're just isolating the flux from the planet from the flux from the stars so that you can estimate the SNR. Okay, okay.
Yeah.
So you were not, because sometimes there are some people who pretend they can like reduce the size of the PSF like to sub lambda over D size. So I was afraid
that's not what we were doing
it would
here.
be something like this, but no, okay, it's more clear now. Thank you.
Yeah. Yep. You're talking about the convolution, I'm aware.
Right, there is still time for one more question. So, who wants to ask the question of the two of you?
Hey, thanks for the lovely talk. I really enjoyed it. I was curious a bit about the PSF as well, in the sense how you describe this process that it broadens with time you observe.
Yeah.
That's generic to any CCD then?
Yes, so the effect has this term called brighter, fatter effect. So the brighter your target, the larger your point spread function will be. It manifests, the details of it are slightly different between CCDs and these types of detectors. So these are impurity band conduction detectors. And so, but it's always an issue. We just did not, because of the physical properties of these detectors, we didn't think we would have that effect, okay? But then I showed that it was still the case. And so I published a paper on the BFE, brighter, fatter effect of MIRI detectors. But it will happen regardless of whether you're using CCDs or other detectors. It's a limitation, yeah.
Oh, okay, thanks.
Yep.
All right, we are at the hour, so we have to stop here, unfortunately, but feel free to bombard Yannis with more questions.
No, thanks.
Thanks, everyone, for coming, and let's thank Yannis again.